Okay, so on to the topic of today. We're going to talk about a strategy of programming more than programming itself, called modular programming. And so we've talked a little bit about the syntax of C++ and a few constructs, but so today is a little bit different. We'll look at a lot of code, but the point here is to set you up in a way that you'll do your coding responsibly. So modularity, as we will see, is necessary because scientific software can be large, complex, and subtle. And so if you put everything that your code is supposed to do in one big int main without trying to divide things up a little bit, it's just going to be unmanageable. So the best way to go about this is actually to section these things off, to find portions of your code that can be bundled together in modules and that you can attack separately and debug separately and track separately, and maybe even give to different people to work on in your lab. So if you don't, if everything is just one big code, everything sort of can see everything else. You might have that variable that you define somewhere in your int main and accidentally use it in another part because it's 1,000 lines long and you can't keep track. So yeah, and so that's this idea of the number of interactions grows as the square of the number of lines of code. So interactions here means if I do something on line n and it's in the same function as 1,000 other lines, then potentially what happens depends on those 1,000 lines. That's the interaction. And I have that for each line in those 1,000 lines, so I have 1,000,000 or 1,000,000/2 possible interactions. And that is really bad when something isn't quite going right. When everything is working hunky-dory and you just write faultless code, no bugs, off the bat always, then this is not the class for you. But these people don't exist. So you have to worry about the fact that if your functions grow too big and something isn't quite right, you'll have a hard time figuring out where the issue is because you have n squared possibilities or interactions to potentially look at. Here is an example of a non-modular code. There's a lot of code here. I'll go through it a little bit, but the most pressing problem here is that it's a code. It does something or would do something if it was complete. There's some dots here that I haven't specified. But it's basically one file. Everything happens here somehow, magically. And it's not that it's bad code. Like what it does fine. So one of the things that's wrong with it is not enough comments. I can't see what it's doing, can't even read what it's doing, so there should be more comments. So I'll speak the comments rather than they be there. So that's one thing that's not right, but that's not the point of today. Today's the modularity is the issue. So imagine that this code computes the ground state energy of the hydrogen atom. And whether it does that or not really depends on what we put in the dot, so that's not really the idea, but that's what it does. And so it has to compute basically an eigenvalue of a matrix, and that's what it does. And there's a function here that's called PW that's doing something that looks like a matrix vector multiplication, or maybe a matrix multiplication, who knows. There's something here that computes, who knows what, it looks like an energy, maybe, I don't know. There's a main routine that fills an M value or M matrix. It calls and then it does something for it. It's not clear what it does, but it does say at the end that it finds a ground state and it produces it and it puts something in files. One big monolithic thing that actually would compile, it's using some libraries, using functions. So those are two things that you would think are modular. I would put some things in functions. PW is here, EN is here. So those are functions. That's modular, right? I've sectioned thing off. I've used some sort of array package not to have to allocate my own. But why is it still so bad? Two things that are wrong with it. So it'll work. It's not the most horrific code in the world, but if this is given to you, as I'm giving it to you right now, you're not going to be very happy. Like your predecessor, PhD student says, "This is what I work on." Now your supervisor says, "Well, now we want the ground state of helium, and you already had the code, so you should be done in a week." No, and a few bad things from a concept of modularity is, first of all, we have these things called global variables. Let me show you where they are. They're right here. These are variables that live outside of any function. That's bad because every function can now use them, which means that although I've sectioned off things uh, in code, so this is about 8 lines, it is about 10 lines, each of these lines can affect each of these lines by writing to these global variables. So I've not modularized it enough because my interactions haven't decreased. Because there's global variables, all the interactions still exist. That's bad. And also, it's actually almost never necessary to have global variables. It's more of a cop-out not to have to pass things to a function. So this function has no arguments, this has no arguments, and it's using these global variables instead. It's not a good idea because it produces these interactions, these dependencies between your code, different parts of code, and that's not good. All the code is in one file, so good luck collaborating on this project. You could say it's a small file, but files never stay small, or projects never stay small. There's no comments. I already said that. That doesn't help us either. So we should. But more importantly, it's really not clear what part does what. It's hardly clear what it does at all. It's not clear what part needs which variable. So with these global variables, we don't know if they're really necessary in every function. The variable names are cryptic, as are the function names. I mean, what does PW mean? What is EN? What are Q, M, N? When we wrote down the math to solve this problem, it was probably clear, and we just took that as is. You should choose your variable names a little bit more carefully to know what's going on. And we have some hard-coded file names, so that's fine. But if I run this again for my helium case, suppose I do succeed in solving that, and I write to the same files, now my hydrogen files are gone. So you'd probably want to fix that too. But it's coded in the code itself, so we'd have to change that and compile it, and there's better ways to do that. So those are a few things that are not so good about this code. I wish I had 2 of these screens and I could put them next to each other. Maybe when I get an upgrade, you can have an even bigger. Is that clear? So there's I'm mentioning these things, and I don't want to be just mentioning negative things, but when you're just starting out, you write your small file. The first time you code something, you're just scared that it works, right? That's if it doesn't work, obviously it's worthless. But just because it works that's not quite enough. So once it's sort of working, you have to pay attention to these things. So that's because you don't write code for the computer. If you're here thinking that you write code for a computer, you're wrong. Code is for humans. The computer understands bits, or maybe bytes if you're lucky. It doesn't care about for or while or main or the names of your variables. The fact that we program in C++, as low level as it might seem sometimes, is really to help us understand what we're telling the computer to do, and not to have to do it in assembly, which people in the good old days had to do. So you write code for humans anyway. There's also no code that is a one-off. If you've ever written a one-off script, haven't you gone back to it? Yes, you have, right? Because either the script worked and was useful, so you want to use it again, or it didn't work, and then it was a write-off rather than a one-off. So code will persist. You will get code from other people, or you will pass on your code, and it just, there's no one-off, so there's no excuse. And even if it is a one-off, you'll come back to it half a year later when you're writing your paper, and you don't understand what it was anymore because you don't know what those variables. So we're going to improve this by using modularity. And so to do that, you want to section things off, and just putting them in functions, as I explained, doesn't help if you have things like global variables. So you really have to enforce sort of boundaries between different parts of the code, and you want to contain create self-contained modules of functionality. The functionality here is essential. That's the only really guideline. And of course, how fine-grained you do this depends. But once you've sectioned things off in some sort of a logical pieces of functionality, you get a lot of added benefits. So first of all, you can treat each of these modules separately. So that's good just for testing. It also, as we will see, makes it faster to compile your code or to recompile your code if you change this one part. It makes it easier to keep track of changes. Maybe the only thing you want to change is how things are written out to file. The rest doesn't matter. That's much easier to do if your file writing routines were in one file and not bothered with any of the other code. So that makes your life easier, and it makes you more productive if you use this modular approach. But it is more work up front. You kind of have to think ahead of time a little bit about sort of the blocks of functionality that you would want. Obviously, there was not much thought that went into the blocks of functionality of the example. But once you've figured out what you want, and so there's a few things that we saw in the code. There was output at the end. There was a matrix that was created. There was some math that was being done. Ground state energies are typically eigenvalues, so somehow an eigenvalue was computed. You couldn't see it from the code. Those are different parts that you could make modules out of. Right? Output, the computation, the initialization, those could all be different modules, functionality. And once you sort of separated those out, you can say, okay, how are the different parts going to work together? So how is the main function going to use the output routines? What does it have to pass to them to make this work? Okay, so how are they going to use, not exactly what they do, but how are they going to be used? So you correct the functionality. What are they going to be used for? When you're making a module anyway, you don't want to make it too general, but you want to think about how it could be used. Do I want it to always write to the same file, or do you want it to be able to give a different file name? That changes what your function would do, your module would do, because now your module has to be able to accept a variable that is the function name. Whereas if you always want to write to the same file, you don't. So you design sort of the interface, the way that you want to be able to use these routines. Now, you won't get this right the first time. You might even occasionally get it completely wrong, but that's okay. Usually what happens after you've done this a few times, you get a sort of a feeling of how it's going to look. And then in the early stages of your code, it will change. You might suddenly realize that you need to add a parameter to your file writing routine to tell it whether or not you should use tabs or spaces in your table. Something like that could happen, right? You don't know everything ahead of time. That's fine. But it won't be too hard to change things as long as the functionality is separated properly. So it's all about sort of an overall design. And we're going to do it on these seemingly silly small problems where you go, well, I can just write the code, but it's going to be the practice of setting things up modularly. It will actually allow this code to grow into any size that you need. So it's time well spent, but no, you have to do it up front. So let's take one example. It's basically the same example as before, but I left out a lot of stuff. If you looked at the previous example carefully, you saw there were two files that were written to, data.bin and data.txt. One is a binary file and the other is an ASCII file. We could take that writing functionality, that output functionality, and make it into a module. It's not the only module we probably make for this problem, but let's see how that would go. Okay? Actually, the easiest to understand because I don't have to do any math. It's just writing. So I took the bits of code in that initial routine and I put them in two functions. One is called toBin and the other is called toASCII. So that's just using functions, right? But I've already decided that I want to be able to control the file name. So there's a first argument that just passes a character string. which is going to be the file name. And then there's going to be an array that I want to write out. And as we discussed last time, when I pass in arrays to a function in C++, it doesn't remember what the size is, so I pass in the size of the array. If I did this properly, those would all be comments here saying and explaining what these different things mean. Fine. Okay, so I'm passing in the array, which means I already decided I'm not going to use global variables. I don't want that. I'm going to pass in whatever has to go out. Nothing in this function uses global variables. It's all defined locally. So toBin defines an output file stream and then writes its data and then closes it. When we go to file.io, we'll explain in detail how it does it, so what it does, but this is now separated out. The ASCII, so the text output is similar. The interface is the same. The only difference is how I print it out. So I can do any file, any array of any length, right? And I don't have to get these from global variables. Then in main, I can just call. So this is just structure programming and just pulling out these functions. But it's the start of a module because these are the only two parts that are really concerned with the output. Right? If I ever wanted to change the outputs, hopefully I won't have to change how they were called. I just have to change. So it makes sense to see if we can't just take these two functions out and make them a separate file. And then only when I have to change the output do I have to go back to that file. That's going to be the idea that we're going to make one module. Yeah. They are essentially the notation of that is the same. When it comes to arguments of a function, C++ doesn't make a distinction between an array and a pointer, and so either or it's the same. Okay, so the first thing to do and to make sure that this works is to use these prototypes or function declarations, as we call them in the first lecture, where we have the same functions. We just put them in the bottom here after in main, which, well, most compilers are clever enough to see where they are, but would potentially mean that when we're compiling in main and the compiler hits toBin, it would say, I don't know what toBin is, because you haven't defined it yet, and would complain. So to make sure that it knows what it is, I put the prototypes at the top. So these are these declarations saying there exists a function called toBin that takes a constant char string, a double pointer, and a number. Just supposing that these exist, and at some point it will find them. Once they are declared, I can use them in the exact way that they have been defined. And then somewhere I still have to define what they do, so the implementation comes in the bottom. This isn't separating out anything yet. This is just the first step in making sure that we do this modular. So the next step is to take the declarations out into what's called a header file. It's called a header file because you'll include that header file in the top of your actual program. So the header file, let's say we called it output array.h, and it just contains the declarations of these functions, not their body, just how they are supposed to be used. So this is the how part of your module. And the hydrogen.ccc file, which was the file that contained in main, will include these. So that once it's included, it basically is as if these two lines were right here. Okay, it includes the file, but didn't include any of the body. And then I can use them. And what we've done here too is stripped out the implementation of these functions, which we'll put in their own file. So we're obviously missing the implementation, but apart from that, this will satisfy the compiler. So it will know I have to call a function that's called this. So this separates the implementation from the interface. The interface is how I'm using these functions, what they are called, what are the input arguments, and what are their return types. Don't need to know anything else for the compiler to be able to compile. I will need to know how they do that once I want to basically create the full application, but for this one file I don't need. So this is often called an API, an application programming interface. Um, it's the interface by which your application communicates with this module. The interface goes into a header file. It's usually called .h. But then the actual code has to go somewhere else. We do have to tell the compiler at the end of the day what these functions do. And so they go into their own function, their own file. It's typically another source file, so .cc or .cpp or .cxx, whatever your favorite extension is. I don't really care. I would suggest you're consistent though, so you don't accidentally end up with a file output array.cc and a file output array.cxx because you pick what you like. So what happens when we compile our code now, our hydrogen.ccc, is that it'll know that these things exist, these functions to bin and to ask that they exist. They'll check whether they are called correctly with the right number of arguments, their types. But it doesn't yet. So this basically gets to be some sort of placeholder in the once it's compiled thing. At some point, please look for these particular functions. But because it can do that. It can use these placeholders. It doesn't need to know the details of the implementation. They are hidden from this source file. So neither the compiler nor the programmer has to know how these things are done. And that's how it becomes a module, right? We've separated the functionality, and when we want to use it, we don't have to know anymore how these things are written out. And we can make things more complex. We can change formats. We can do all of that, and the main program doesn't have to care about that at all. It's separate functionality. So before, however, we can create an actual application, we have to get back those definitions. So they're in a different source file. So every source file will have to be compiled. So there's two source files now. There's output array.cc, which is the definitions, so the functions with their body, with the actual for loop, etc. And we have to compile the header. But since neither of them is a complete program, output array, for instance, will not contain a main program. There's only one main function that can be in your application. We have that in the hydrogen.ccc. The output array.ccc will not contain a main function. If it doesn't contain a main function, it's not a valid C++ program that can be compiled into an application or an executable. Instead, it gets compiled into what's called an object file. So it's basically almost an application, except it doesn't have an in main. You can think of it that way. And it might call functions that aren't in the same file yet. So I have this intermediate object file that compile the code that I can see, put in links to functions that I don't see yet, and leaves it at that. So I do that with both these files, and then there's a thing called a linking step, where it takes these object files and tries to resolve these placeholders or these pointers to functions that are supposed to be elsewhere. So in the linking phase, these placeholders, these pointers to the functions to bin and to ask, are going to be resolved by finding them in another object file. So I take all the object files together, and it basically links them together. Once that's done, I have all the information to create an output file or an application. Tell the compiler not to do this linking. You have to give it a -c flag. This is compile only, and that creates the object files. At least in Linux, are traditionally called .o, just so you know what they are. Stick to that convention. Right? Okay, so two files, both are compiled to their object codes, and then they're linked together, again by the compiler. Now, there's actually another program that is doing the actual linking, but the compiler can call that one, so we don't have to think about which is my linking program, which is my compilation. Step, a little bit clear. So I've separated out into different source files. The header file, in a sense, is the glue in terms of the compilation, but at the end of the day, the linker makes sure that all of these functions are found again. Kind of looks like this in a more complicated case where I have several CC files. So I can have some header files that basically are included in CC files. And each of these CC files has to be compiled into an object code, and they have to be linked together to the executable. So that's the flow. This is the build tree. There can be some object files that already existed that we don't have to build. They're typically called libraries, and there's in Linux two kinds. There's the .a and the .so. Well, let's not go into the detail of that right now, but you'll have to link them in if you call external routines that you didn't write. So you specify in the linking stage all the object files and any other libraries, and you get that executed. Here's your source. It's nicely modularized. You tell the compiler to do this compilation, and then you tell the compiler to link them together. You'll always have some .h's that are system headers, at least. And if you don't have a .h, so let's look at the code. If I didn't have this .h, int main would have no way to know that this function exists. So basically, the compiler would say these are not defined. So you need the header files as an interface to tell your code, these functions exist. I won't tell you what they do, but this is what they look like. So that they can put in the reference, and that can be resolved at linking. Okay, so you will need header files if you're doing modular. They are your interface. Okay, so that's now this looks complicated. We'll see in a few lectures how this will actually be very manageable. It doesn't mean you're doing a lot more typing of compilation commands. You can automate this, so we'll see how to do that. Now, I have these header files here. It's important, just from the start, because otherwise you'll forget, to protect your header files, by which I mean you can have header files that include other header files. It's actually very common. Maybe one header file uses a particular data structure that's defined in another header file. Now, so let's call an example. This one doesn't have it, but suppose that rather than putting in a character string, we put a character pointer, we put in a string. A string is defined in another header file called string. I would have to include that header file here. What if that string header file was also trying to include output array.h? Okay, it's a little bit far-fetched here, but you would have a circular inclusion, and you'd have your compiler include a file into another file into another file, and just goes down and down and down and down. Whereas the only point of a header file is to define things. Once they're defined, you don't have to define them again. So you can make sure that your headers are only read once, so that everything is defined or declared only once by using these guards. This is called a header guard. And it uses preprocessor commands, which can define sort of on a meta level, can define constants. So what this does is it checks when it's reading in this file. This is something that doesn't happen in execution, just in compilation. When it's compiled, the compiler reads the file and checks if there is a preprocessor constant called output array _h defined. And if it's not defined, that's this little n here, it defines it, and then defines these two functions. If to make sure that this is blocked out. If I try to include output.h twice, I could do it explicitly by saying found includes output array.h, and then again found includes output array.h. The second one would fail, or not fail. It would do the following. It would already have defined this constant, and so the second time that the compiler reads it, goes, oh, this is already defined, so I'm going to skip this section. It's a very common thing to do to make sure that your headers are included only once. You should do it because it's safe, and at some point your headers are going to include other headers, are going to include other headers. Infinite recursion won't occur if you do it. A quick note about preprocessors. There is a program that's not a compiler, but that's more of a text processing, very, very, very rudimentary text preprocessing utility called a preprocessor. They can do things like define constants and do some. It's yeah, sorry. Mm-hmm. No, at the end of your header file. So this is a header file that only contains the declarations, right? So you put it at the end, yes, but it shouldn't be a very large file typically. So the same preprocessor, so the preprocessor syntax is always this pound sign, and so the pound includes command or construction is actually also a preprocessor thing, so the preprocessor thing. So the preprocessor reads in those files and includes them, and then gives them to the compiler as if they were just there. So it's not a very sophisticated or intelligent bit of machinery, but it is essential for just those two things, really, to make sure you include the files and to make sure that they only get included once. You can use them for other things too. I would try and shy away from this. There's no need to use them to define constants because there's a const keyword in C++. It's another common thing to do, but it really isn't necessary. But these are two things that you can do just by the compilation because they really treat the files rather than the language, and the compilers for the language. It doesn't matter. You can make it. You're going to want to make it likely unique within your project. So I tend to base them on the file name, and the fact that I do _h is just something I like to do, but it doesn't. Output_array.h. Yes, yes. So you don't have to. So only. Yeah. About what is output array. No, it's just a tag, basically, a preprocessor tag. That it is true that you could use it, like your code could check if it is also defined, but that's the kind of trickery that I advise against. So it's really you have to think of them as living on a higher level outside of your code. They are just there to make sure your file processing goes properly. And if you do that, then then they don't interfere, because these are essentially global. So it's all the bad stuff. So you want to only use them for this. Okay, so the header files are protected. They have to have the definitions. The implementation goes into a different file. So let's talk a little bit about what exactly you do and do not put in a header file versus the source file, because you'll start off with some code that is just one big chunk. So what do I put where? So in the very least, this header file has to have the function prototype. This is the interface, the API. How can these functions be used, and what are they called, so that later I can find them when I link them. So you can't rename a function. The function has it. That has to be the least that's in there, right? Might be some other stuff that can also go in there. There might be constants that you define that sort of signals something. You could imagine that you might have a constant that you pass to the output routine that says whether or not use tabs or spaces, and tabs might be denoted by a 0 and spaces by 1. If that's the way you've designed your API, there should be constants that are defined there that have the values 0 and 1 that signify this meaning. So there could be constants there. Another thing that could happen is you could have data structures that you define that are used. Those data structures will have to be defined in the header file. When we talk about data structures, it'll be a little bit clearer. Not every header file will need those. All header files will need some function prototype. Now, to work, header files don't have to have comments, but of course, for us to be able to read them, there should be some comments. Give a description of the module, give a description of each of the functions. What do the parameters mean? The header file is a good spot to do that because you'll need that header file to know what's going on. Hopefully, at some point, you'll write proper documentation for your modules, and you'll have a document explaining this too. But programmers really just like to look at the code because they think they're smart, and so they'll figure out what's happening from the code. They look at the header file. If it has a comment there, you've helped them out, right? So that goes into the header file, and pretty much nothing else. Okay. One thing that you should know that does not go in there are variables. Don't put variables in your header file. Essentially, you'd have global variables, which is bad to begin with. But it also means that each time you include this header file in different files, you'd have two versions of these variables for each of the codes. No variables. That's something that. What else? When you're doing your modular design, we've done one header file and one source file. The one header file should be a golden rule. For each module, for each piece of functionality, there should be one header file. The header files can have 10 functions in them, but they all should sort of fit together and have a common purpose. In theory, you could have multiple source files. This can be useful mostly for compilation optimization. So each of these files, each of these functions defined in your header file could be in a different source file. Not how you would start out. It's not necessarily the best thing to do unless it really grows. But you could do that. However, don't spread out your header files over different modules, or in a module over different header files. You also don't have to have every function prototype in a header file, only the ones that you expect to be used when your module is used. So is there some internal function in the module that's called by your functions? Yes, it will be in the source file. It doesn't have to be the header file. So suppose there is a specific function that writes a space to a file. A little bit silly. But we don't want people to use that, like programmers to use it on the outside. It's just used within our own functions. Then we only have to have that function in the implementation. It doesn't have to be in the interface. It doesn't have to be in the header file. Not everything that's in your source file has to have a prototype in a header file. Only those that are needed for using the module. Okay. So that you tell it that by doing the pound include. If you don't pound include, it will not read them. So this line pound include has to be part of the hydrogen.cc. Otherwise, it will not be read, and the compiler will not know that these things exist. So you have to put that in. That's actually one of the reasons why you want to keep the header file just having the bare minimum things that are necessary, because you don't really see it anymore, but these are essentially still plugged in here. So you'll get more lines in your code, and you get these interaction effects again. So just the interface. All the rest goes in the source file. So the implementation of the functions, any internal routines like this sophisticated space writing routine. Another thing that I find very useful to do is, although it's not necessary, is to put the .h file of that module at the top of your source file. And what that does is it declares that those functions are there, and the compiler will then check when the functions are actually implemented that they are of the right type. So it will see that the number of arguments is correct, or that the number of so it'll detect inconsistencies. Otherwise, you can just define your function there, and it might be a completely different function from the one that that was in the header file. The number of arguments might not match. And then basically anything that you need to compile this piece of software goes in the source. So that's we'll likely ask you to take some code and make it modular. That's how you separate things out. Sure. It's something you kind of have to do it. One thing that I would encourage you to do, and you'll see that when you get your homework back, we will seem to be overly critical and nitpicking. That's just meant to give you proper feedback. Most of the nitpicks will either have no points deducted or very small. We just want to make you into better programmers. We're the only ones seeing this, and we won't tell anybody else if your coding style starts off a little bit. And so don't be shy, okay? We're discreet. We won't tell anybody, oh, he's such a bad programmer. His comments are, he doesn't have punctuation in his grammar. Like, no, okay? But don't be shy. Just try it, because the only way you really learn this stuff is to do it wrong a few times. We expect most of you to have many comments in the first few submissions, and that's just, that's fine. That's the learning experience. You'll find that it helps you. We want you to learn. We don't want you to do a perfect job right away, because then you wouldn't have to. Okay, so let's end with a few benefits, because this seems like quite a bit of work, just especially for smaller projects to do. So I want to reiterate what we really get out of this, and it really is sort of a long-term. They're long-term benefits. They're like your pension plan for your code. So if you don't have a modular code, we just have one file, and you were given this one file, you'd have a hard time figuring out what's going on. You saw that. If it's modular, even just having it separated in different functions gives me an idea of what's going on here. There's my main code still, but there's something that writes out an array, something that creates that computes eigenvalues, something that initializes the matrix. If that's how it was set up, that helps me already sort of getting a grip on what this code does. And if I were asked to change something, I would know better what file to start looking at. I don't have to look at all of the code right away. So very, very useful for maintenance. This make file we'll see the next time, or the day. We'll see is a file that helps you compile all of this, so you don't have to do all of the compilation commands yourself. So we'll see next time why that is useful. So each of these files has its own responsibility. There's one for output, there's one for creating the matrix, one for the eigenvalues. So that's useful to understand things. Also for your future self. Your future self is not as clever as you think, and will have forgotten all of the tricks that you put in there. So don't be too clever. So clearer means easier to maintain and adapt for the future. Another benefit is the speed by which you can compile. So if I have this build tree again, and assuming I have this make file to help me do this, what it can do is it can actually parallel process these files, because each of the .cc file compilations into the .o file is now independent. If I have everything in one file, it has to read it from top to bottom. It has no choice, right? So it's one line. If I have a multi-core machine, I could have 5 cores. So you have 5 cores. That's a funny machine. 5 cores running these at the same time would be 5 times faster. In the linking phase, they will all have to resolve again. But that's typically not the hardest, the slowest part. It's figuring out the syntax and what you mean, variables, etc. So we can parallel process the code. And similarly, if you only changed one file, say here's my output file .cc, and I either changed something because I wanted to add functionality, or I changed something because there was a bug, only this .cc file has to be compiled. All of the other stuff doesn't have to be touched. And so it compiles that one and then does the linking again. So it's faster rebuild than having one big code that goes linearly. That's good. And we'll see next time how you can use the utility called make to enable this, rather than having to figure out yourself what to recompile. You can do better version control. We'll have a whole lecture on version control with Git. But version control systems essentially track files for changes. And especially when these are text files, such as code, you'll actually track the changes line by line. So we'll know, okay, at this date, this line in this file was changed. There's some manual intervention to make it track it that way, but we'll see how to do that. But if these are different files, I can actually track whether I change something in the output, in the computation. So it's a more fine-grained version control, rather than just saying I changed the file a week ago and it doesn't work anymore. So it's easier to restore functionality. So say something broke. You were working on the code, maybe did a bunch of things broke. You know what's going on. You could one by one restore your old files and see which one is the culprit, rather than having no choice but to go to completely the old version, and you still don't know which of the 5,000 lines is. And then finally, and we'll talk about this too in a separate lecture, having these modules not interact makes it easier to test them, and also easier to reuse them. So once you have a module that can do a certain task, you can basically see it as its own quantity. So each function separately there can be tested. You can see if it does what it's supposed to be done, supposed to do in a controlled environment, rather than having just this one application code that at some point breaks. Something breaks. Who did it? What's wrong? I can test the different pieces separately. And I can do that because they're modules. They don't rely on the rest of the code base. They're just a separate function, and I can give them some test input, and I know what's supposed to come out, and I can check that. So it's easier to test. When you just have one code, you can only, it either works or it doesn't work, and you don't have it. And then once you have this working module, you can use it in other projects. So this other project that really wants to write things in binary and is also a vector, just take that code, and use it again. I don't have to develop it. I don't have to worry about it interacting with other parts of the code because I know what the interface is. And as long as that's properly commented and I know what those arguments mean, I just reuse it. Okay. So modular programming is the way to go in anything that is moderately complex and does more than one thing. And no, this doesn't depend on compiled language. Scripts are the same. You can almost any scripting language allows modules. Python are you can write your own they might be called packages, but they're still just separate files that you put some of the code in. Depending on the language, it either does or does not allow the separation of interface and implementation. So in Python, by default, any Python file can be a module, but you don't have this idea of declaring the function and then defining it later. So it doesn't do that almost on purpose. Whereas in most compiled languages, you will have that because you know in compiled languages there is this linking space anyway at the end. So that allows this separation. Okay. All right.